splitting field. P now is some polynomial with coefficients and k not necessarily reducible. Definition: a splitting field of P over K is a field, an extension, where P is split that is to say, is a product of linear factors and, well, let me give it a name, L, and the roots of P generate L. So let's say it's the smallest field extension where P is split. Theorem. Theorem 1, I think. A splitting field exists. Splitting field exists, and its degree over K is less or equal than g factorial, where g is the degree of P. Secondly, it is unique up to an isomorphism if L, L prime are two splitting fields then they are isomorphic as K algebras but such an isomorphism will not necessarily be unique. We shall prove this theorem by induction on D. Well, if D is equal to 1, everything is trivial. Any splitting field is just K itself. So let me suppose that D is greater than 1 and theorem is proved for all polynomials of degree strictly less than D over any field K. Then what we do is we take an irreducible factor Q of P. And let alpha be a root. So L is K of alpha, L1, sorry, K of alpha is a stem field of Q. So over L1, we have P is x minus alpha times R. And we know that we have a splitting field of R over L1 and its degree is at most degree of R factorial. But the degree of R is at most d minus 1. So this splitting field of R over L1 will be also a splitting field of P over K. And the degree, well, let us give it a name. Why not L? This L will be a splitting field of P over K, and its degree is equal to L over L1 times L1 over K. So, of course, it's less or equal than d minus 1 factorial times d, which is d factorial. Okay. Now it remains to prove uniqueness. Well, uniqueness up to isomorphism. Let L and L prime be two splitting fields. Or maybe, let me better call it M, the other one, because I already have L1 and this might be confusing. L and M be two splitting fields. Now let beta be a root of Q in M. Well, Q was some irreducible factor of P. Then K alpha, which is L1, and K beta are both stem fields for Q. So we have an isomorphism phi from K alpha to K beta, which sends alpha to beta. Now P is x minus beta times S in M of x. So where S is phi of R. So M is a splitting field of S, of course, over K of beta. M is an extension of K of beta. But now let's remember that we have also defined a field extension as an algebra. But M is also a K of alpha algebra via phi. K of alpha acts on M via phi, which identifies it to K of beta. And as such, it is a splitting field of R over K of alpha. Well, I know you have to meditate about this a little bit, but this is true. As soon as you view M as a K algebra, you sort of take this phi into account. So M is also a splitting field of R over K alpha. So by induction, we have K of alpha isomorphism from L to M. And of course, we also have a K isomorphism. K isomorphism between L and M. So, remark, the isomorphism is of course not unique. This isomorphism between two splitting fields is not unique. A splitting field, in particular, can have many automorphisms, many K automorphisms. And in fact, the objective of Galois theory is to study this group of automorphisms. This is, in fact, the subject of Galois theory, which you will see in a couple of lectures.